So let's go through a sequential multiple regression analysis. As we noted in our last video, we'll enter the variables into our regression model in a series of successive steps. But unlike stepwise multiple regression, where it's completely data-driven based on which variable has the biggest effect, we're now going to enter variables in a causal sequential order based on a theory or a model. So here's the model we developed in our last video. Again, for continuity and to contrast the differences, we're reanalyzing the data that we've been using for simultaneous and stepwise multiple regression, but we're not including father's education in order to keep things a little more simple and straightforward and make the process a little more clear at this point. Notice that there is an inherent sequence of effects in our model. Our analysis will exactly follow that sequence. The first variable is mother's education. Mother's education has an effect on the other variables, but notice in our model, nothing has an effect on mother's education. There are no arrows pointing to mother's education. Causal arrows only go from mother's education to the other variables. And if you look closely at those arrows, you'll notice that the next variable in our causal sequence is school quality. It's only influenced by mother's education, nothing else. So that will be the second variable we add to our model. Then our third variable is study hours. Notice both mother's education and school quality influence how many hours a student studies. And all three of our predictors influence or cause our outcome grades. Okay, so that's our model. Let's begin our analysis with model 1, in which case all we have is mother's education in the analysis. Okay, so here's our ANOVA table. We see that the team of variables that's made up of, well, mom's education all on its own at this point, is statistically significant with an F with 1 and 398 degrees of freedom equal to 58.259 and a P less than 0.001. In the model summary table, we see that this effect, just mom's education on its own, accounts for 12.8% of the variance in grades. This 12.8% of the variance is the total effect for mother's education. Remember, the total effect of a variable is the effect it has at the point it's entered into the model before other variables have been added after it. And remember, the total effect is the sum of a variable's direct effect and any indirect effects it has through other variables. Now, of course, there are no indirect effects yet because there's no other variables in the model, right? It's just mom's education. But if those indirect effects actually exist, those indirect effects are here. They're part of that 12.8% of the variance. They're part of the total effect. We just can't see them yet until we add more variables to the model. And of course, the total R squared and the change in R squared for the first model are the same thing because the change from no model to model 1 is model 1, right? But just for the fun of it, let's take a quick run through the formula for calculating the F-test for the change in R squared while we're here, okay? The formula for the F-test for the change in R squared is the R squared new, the R squared for our current model, minus the R squared old, the R squared for the previous model, divided by K new, the number of variables in our current model, minus K old, the number of variables in the previous model. All of that divided by 1 minus the R squared for our current model, divided by n minus the number of variables in our current model minus 1. If we do that, plug in the numbers, this works out to 0.128 minus 0 divided by 1 minus 0. All of that over 1 minus 0.128 divided by 400 minus 1 minus 1, which is 58.259. We write that out as the f sub delta r squared with 1 and 398 degrees of freedom equals 58.259 with a p less than 0.001. Now, in practice, you don't have to write that delta r squared subscript for the f-test in this case, but for us, at this point, I like to include it for clarity, particularly when we get into higher models of Models 2 and Model 3. Okay, so we'll keep it there for now. Let's look at a Venn diagram for the model. Now, at this point, it's very simple, right? While things are not drawn to scale, the area of that overlapping variance is 0.128, which is our r squared, which reflects 12.8% of the variance in grades is related to mother's education. Now, this may seem silly at this point, but as we go through the analysis, I'm going to write an equation reflecting the total r squared at each step so that we can see how it changes as we add variables. Now, of course, in Model 1, it's very simple. We're predicting the r squared for grades based on mother's education. That's what the grades.education mom means in the subscript. Grades is our outcome. We're predicting it based on mother's education. And that's equal to the r squared for grades based on mother's education. Or 0.128 equals 0.128. Now, like I said, it's kind of silly at this point, but you'll see where this is headed in Model 2 when we add a second predictor. For now, notice how that blue r squared based only on mom's education in the formula is the blue shaded overlapping area in the Venn diagram. And again, as we noted previously, this is the total effect for mother's education, right? Now, let's look at the coefficients table. Again, focusing on Model 1 for now. We see that our unstandardized coefficient, our b, tells us that a 1 unit increase in mother's education is related to a 0.131 unit increase in grades, which is statistically significant with a t with 398 degrees of freedom equal to 7.633 and a p less than 0.001. Looking at our standardized coefficient, our beta, we see that we can say the same thing just in terms of standard deviations, as a 1 standard deviation increase in mother's education is related to a 0.357 standard deviation increase in grades, which is statistically significant with the same t-test and p-value because it's the same effect, just described in different units. And we previously just used the Venn diagram to visualize our model. We can also visualize it using a path or causal model just for Model 1 in this case. At this point, right, it's pretty simple, right? Now note that we typically describe the size of the effects in the path models using standardized coefficients or betas. So the path in this model is equal to the beta for mother's education in Model 1. Later on, when we cover path analysis, we'll see why we use betas. Okay? So again, this beta of 0.357 reflects the total effect of mother's education. And again, the total effect of a variable is seen in the effect that it has at the step it's entered into our model. This is where we've entered mom's education, right? And it's before we've added any of the other future variables into the model. Now remember, the total effect is equal to the direct effect plus any indirect effects. But in this model, there are no indirect effects yet, are there? There are no other predictors, so we can't have any indirect effects. As a result, at this point, the total effect is the direct effect, or you can think of it as the direct effect is the total effect. That's all there is. Now, to be clear, what I mean is that there are no measurable indirect effects. For example, let's say mother's education may have an indirect effect through school quality, but without school quality in the model, we can't detect it as an indirect effect. It's there. It's happening. It's having an effect in the data. I just can't distinguish it as an indirect effect. It's buried, it's hidden, it's smushed into that B of 0.357. It's part of that total effect. But as we add variables, what we're going to see is that we'll be able to pull out the indirect effects of those variables and split that total effect of 0.357 into separate direct and indirect effects. And that's where things, in my opinion, really start to get interesting. I mean, sure, that beta of 0.357 is the total effect of mother's education. That's good to know. But without other variables, we're left wondering why, or how is it having an effect? What's the process for this effect? Is it mom genes, genes with the G, and unrelated to other environmental factors? Is it the environment around the child? Picking the right school, what goes on in the school? Is it reading in the home? We know there's an effect, but we have no deeper understanding of why. What's the process through which this effect is occurring? We'll start to see that in our next video when we continue our sequential multiple regression. But for now, let's say goodbye. See you in the next video.